Well, good morning, everybody, and welcome to the investigation of the impact and management of harmonic distortion for large renewable energy generators. My name is Dwayne Robinson, and I'm the Director of the Australian Power Quality and Reliability Centre here at the University of Wollongong. I'm joined today by my colleagues Jason David, who is one of our research fellows, and Sean Elphick, who is our research coordinator of the centre, along with yourselves, of course. And we'll be running through this workshop from now through to somewhere around about 12 o'clock today. We understand that people might come and go as they please. Just a few logistical things before we start in. As I mentioned, first of all, we will be recording this particular presentation, so we will make it available for people to view at a later date if you do have to step away. So for those people who are attended and want to see it at a later date, we'll certainly make that available. The second thing is we're just going to keep everybody muted through the presentation other than ourselves as presenters. I'll talk a little bit about the logistics when I get to the program as well. So I just wanted to kick off firstly by just giving a brief introduction to our centre here. So the Power Quality, Australian Power Quality and Reliability Centre was first put together as a partnership with Endeavour Energy here at the University of Wollongong way back in 1996 to conduct research in the field of power quality. Generally speaking, we work with generators, transmission and distribution network service providers, as well as heavy industry or any connected industrial customers, but all the way down to, I guess, residential customers as well, on research projects here at the University of Wollongong and have done over that 25, nearly 26-year period now. The research centre itself it's a relatively small research group. We have around 8 staff members, nearly 20 higher degree research students doing their PhD or Masters by research, as well as nearly 20 honorary or visiting fellows, some of those who have joined us here today as well. As a centre, we've always prided ourselves on having a very strong connection with industry, and that helps shape our very focused research towards the electricity distribution area. I could mention a couple of other major projects that we've got on the run at the moment, but I'll leave that for another time. Just from the point of view of the activities at the centre, I've already mentioned a brief introduction to our research activities. One of the other key things that we do from an educational point of view is we're involved obviously with the undergraduate and postgraduate teaching here at the University of Wollongong, including our Masters of Electrical Power Engineering and graduate certificate in the same topic area. But we also run a number of continuing professional development courses or continuing education courses for industry people like yourselves. So if you're interested in attending any of those courses in regards to electricity distribution and or power quality, then please have a look at our website and you'll see more details in that regards. The other thing that takes up a lot of our time is the consulting activities that we do with all our industry partners. So that includes investigation into power quality problems, monitoring exercises. We have a lot of mobile kit available to go out and do power quality monitoring, both in all aspects of power quality, including sags, harmonic flicker, etc. And as per the project that we're about to present on today, a lot of both our research and our consulting activities have been heavily focused on renewable energy generation systems and their connections into the grid. And I guess the other strength of the centre that I'll mention today is that we do contribute a lot to the development of both Australian and international standards related to power quality. And of course, we have a number of software platforms available to both validate, analyse and verify our research. So jumping into the project for today, as I mentioned, Jason David and Sean Elphick will be taking us through the contents of this particular workshop. So Jason's going to provide us with a project introduction, just over a period of about 10 minutes, trying to adhere to our time. And then we're going to step through the 5 different phases of the project that we're reporting on in this workshop. So those 5 phases are content 2 through to 6 on the slide that you've got in front of you at the moment. So the project introduction will probably take Jason around about 10 minutes. And then we'll have about an hour from Jason stepping through the contents 2 through to 5 there, at which point we will have a 10-minute break for everyone. And so then we'll come back and Sean will present topic 6 there, and then topic 7 and next steps. So looking at what do we do beyond this project, or what needs to be done in regards to harmonics in our transmission and distribution systems. And then we'll have an additional 10 minutes for questions after that, just on all those content items. And then we'll open the floor up to some open discussion. So the open discussion should start around about 11 o'clock according to our program, assuming that we stick to time. I guess the time's a little bit variable depending on questions that we run through. I will mention at this stage, if you, from a point of view of asking questions through the presentations, we would ask that we restrict questions to the chat. So we'll monitor that as we go through. We will also pause at the end of the sections listed on the contents there. So after each one, Jason will pause for the first 4 and Sean for the last one, just to field some of those questions from the chat in a very brief manner. And if we need to carry them through to the end, we'll do that. Also to make sure that we answer as many questions as we can. And other than that, as I mentioned right at the start, in case those people that are just joining us, we are recording this session, and that will include all the chat questions as well. So just to remind you of that. So that's the program for today. I would also like to take just a little bit of time to thank the sponsors of the project. Obviously, the Australian Renewable Energy Agency was the main contributor to this project, so we thank them for their support throughout the project. But we've also got a number of industry partners who are involved with the project, and that they are listed on the page there. So Essential Energy, Endeavour Energy, Electronet, Neoen, RES, Transgrid, and Vestas, all very important contributors to the project. Both from the point of view of helping us fund the exercise, but also from the very important feedback that we got from all of our colleagues within those organisations, and also their data from the field as well for wherever it was relevant. Finally, just before I hand over to Jason, this workshop is obviously a bit over an hour summary of everything that we did. The technical details of everything within the project are available via the ARENA website. So there is a full technical report, but also a brief summary of the project overall available from the ARENA website. If you just search for harmonics, there's not too many projects within the ARENA bag in regards to harmonic management, so you should find it relatively easy. And the more detailed presentations, some of which you see on the screen at the moment, they're all available from the Australian Power Quality and Reliability website, which we will throw into the chat for you to link to, because I didn't include it on the slide here, which is a mistake on my part, but we'll put that in the chat so you can quickly click to there and you can find the details of the remaining publications not already on the ARENA website. Okay, so welcome again from myself. I'm now going to hand over to Jason David to begin his presentation. So over to you, and thank you, Jason.
Thank you very much, Dwayne, and good morning to everyone, and thank you very much for joining. So we've got quite a good attendance, so obviously hitting a chord of some degree. So briefly, we'll just be looking at a brief introduction of the project. There is some assumed knowledge, I suppose, in terms of harmonic distortion. I guess assuming that you've signed up for a 3-hour workshop, so we guess that you've got some level of interest and understanding of the topic area. But really, what we're looking at here is harmonic distortion in a long-term analysis. So we're talking about long-term impacts, probabilistic assessment, 95th percentile values, those sorts of things. So harmonic distortion ultimately will increase losses within the power system. In some extreme cases, it can actually lead to catastrophic failure. In the examples of, say, capacitor banks aligning with resonances in the power system, and even in some cases, instability, particularly with power electronic controllers and interactions between individual devices themselves. So it's important that NSPs have a good handle on the voltage distortion that exists on their power system, but it's also required by law that power system harmonic voltage distortion is managed. And really what we can show is that inefficient management strategies that are commonly in use are capable of increasing the likelihood of mitigation that is required by the customers, ultimately increasing costs for renewable energy, but also generally any connecting customer. And all of this can lead to an increased complexity of operation and management of harmonic distortion in the network, and ultimately leading to things like shifting resonant frequencies and ultimately impacting the wider connected area. So we know that there's an ongoing connection of renewable energy generation that is occurring, not just here in Australia, but also globally. This is something that's happening everywhere. And by and large, these are inverter-based resources or inverters, solar farm inverters and wind turbine generator inverters and battery inverters, HVDC, all sorts of things. And these connections are commonly occurring in fairly weak areas or areas where the management of power system impedance may actually be a little bit more difficult. And being electrically distant from synchronous generation, which is capable of actually sinking harmonic currents and keeping voltage distortion to a reasonable level. One other note that I'll refer to is that the Australian standard that is currently in use and currently referred to in the National Electricity Rules was developed in 1996. It was adopted by Australian Standards in 2001. And this is the document that is referred to in the National Electricity Rules. And so we know that there's been a lot of changes since 2001 and 1996. And so we're looking into the potential that, well, perhaps it's the processes are no longer really fit for purpose, and perhaps need a good thinking about. So some of the issues, and we'll go into a bit more detail in following slides, but some of the issues in the outset that were really identified was one, the sheer amount of renewable energy generation that is not only connected, but is expected to connect. Anyone familiar with the integrated system plan of AEMO, we're expecting hundreds of gigawatts in the next 30 odd years. So that's obviously going to have a large impact, as mentioned. Quite often these installations are inherently emitting harmonic emissions. So managing these emissions appropriately is certainly of importance. Added to that is a degree of uncertainty. So the IEC, or the Australian standard for managing harmonic emissions, ultimately requires some level of forethought and forecasting of a network. With the rapidly changing expectations of the network, the impacts of uncertainty are definitely something that needs to be thought about and considered in the management process itself. Other issues such as non-characteristic harmonic orders, so the development and the management of harmonic distortion ultimately prioritises a subsect of harmonic orders, but what we're seeing is that present day technology and emerging technologies are actually quite high, or comparatively high emitters of non-harmonic orders, non-characteristic harmonic orders, and so consideration of these sorts of emissions needs to be thought about. Also looking at networks, particularly here in Australia, with networks with long feeders and transmission systems with resonances, and ultimately the overall impact on network harmonic impedance and how we best manage distortion in such scenarios. So the high level aim of the project itself is to really critically review Australian harmonic management processes, and picking out particular areas where improvements may be made, even if they are only marginal improvements, but really spend a good amount of resources on how best to even just think about these sorts of issues and how one might actually approach improving what is actually being done. And obviously with a specific emphasis on conditions with renewable energy generators being connected. So the key research activities, these we'll be going through these in detail today, but as Dwayne mentioned, there is also a lot of resources online and openly available on the ARENA website, that will provide you with specific studies and also the overall project report, which provides all of this in quite a lot of detail. So step number one was to really assess the level of harmonic distortion and trends of harmonic distortion over the past couple of decades, really just to see what harmonic distortion is doing and identify what impacts renewable generation has actually had on distortion, given that the number of harmonic sources is actually increasing, and seeing what the trends are actually doing over this time. We then looked at a review of the International Harmonic Emission Allocation Procedures, so how networks actually allocate emission limits to individual customers. So this was ultimately quite a detailed literature review, along with some, I suppose, some high-level outcomes and some ways that we identified that may be suitable to actually deal with the impacts that we've detected and the issues that we have identified to be important. Next, we looked at an investigation of harmonic source aggregation. So anyone familiar with harmonic modelling and compliance assessment, something called the summation law or the alpha law or harmonic aggregation, however you want to call it. There's a suggestion that individual harmonic sources will aggregate in some particular way, which may not always ultimately lead to an arithmetic summation. So we looked at some empirical data that were able to actually identify levels of diversity between harmonic sources. We then looked at a review of the strategy of mitigation, how it's applied here in Australia, and also investigated perhaps some efficiencies that may be introduced or some improvements that may be made in the current process, and that was actually quite an interesting outcome of that study. And also a very preliminary evaluation of compliance assessment. So that's both pre-connection compliance assessment and also post-connection compliance assessment, and really, I suppose, identified a shopping list of challenges in the practical assessment of compliance. So these will all be we'll be going through in detail. So work package number one was the review of distortion levels worldwide. Those first few points we've already discussed, but really what is an important point to make is that the connection of renewable energy is ultimately leading to synchronous generation becoming less economically viable. So we've already seen here in Australia over the past 12 months the announcement of early retirement of thermal generation that is occurring, and it seems to continue to occur. And so that will ultimately remove large synchronous machines that exist on the network that act as absorption or sponges almost of harmonic current, capable of managing the harmonic voltage in the network. And so what we're seeing ultimately is that networks are becoming ultimately weaker, and that will have an impact on the harmonic impedance of the network. And as already mentioned, quite often the renewable energy generation will connect via a power electronic interface, which are inherent sources of harmonic current. So it's fair to assume that with all of these things happening, we would expect that harmonic voltage distortion in general may increase as connections continue to be made and retirement of synchronous generation is occurring. So we looked at some long-term data that we had available to us. There were two databases that were drawn upon. One that is managed here at the University of Wollongong. Some of you may be aware of the Power Quality Compliance Audit, which is run by the Australian Power Quality and Reliability Centre. Now, what we were able to do was look at particular sites in which we had data both pre and post connection of some renewable energy generators, and started to look at the 95th percentile impact ultimately of each of the sites. Sorry. And there was also another database which is publicly available. This is not drawn on research agreements or industry contacts or anything. This is a website that is openly available to anyone, and it's run by a consortium, I believe, of Dutch TSO's and potentially DSO's, and the title given Netbeheer Nederland. So this database ultimately gave us access to long-term THD trends. And again, we were required to identify particular sites that we were interested in. And those sites were ultimately ones with enough data, both pre and post large renewable generators being connected. Anyone familiar with the Dutch system is there's quite a lot of offshore wind that has been and is being connected in the future. So it's quite a valuable source of information there. So firstly, the Australian data. So this is the PQCA data that was drawn upon, and also some data that was provided by some of the project partners. But ultimately the process was the same, very simplistic. We're looking at statistical impacts here, very slow changes. So we're assessing 10-minute values, as you can see the time series representation. And ultimately we would define a 95th percentile value for an out of service time period, and a 95th percentile value for in-service period, as you can kind of see in the graph there. And using a very simple equation of in-service minus out-of-service values just to assess an estimated impact or a change in harmonic voltage distortion during the connection of the installation itself. And so based on this, a negative value or a negative result will ultimately suggest that post-connection levels are actually lower than pre-connection levels. So what we see here is that, well, firstly, any harmonic orders with an increase are quite limited in the actual impact that was detected for this particular wind farm. Now the wind farm, I believe, was about 120 megawatts. I double checked that overnight. It's around 120 megawatts. We're not sure of exactly where it is connected. We were given this data anonymously, or the actual details of the data was made anonymous. But what we can see is that the pre-connection voltage levels compared with the post-connection, so at the fifth order, we see a slight increase of about 0.1% across the three phases. And for all others, the impacts are restricted to less than 0.05% of the nominal, other than the 7th, in which we actually see some attenuation. And so there's actually quite a relative improvement at the 7th. Reasons for this, we can't say for sure. Like I say, there was very little detail that was provided to us in respect to the actual installation itself. All we can see is simply the measurement data and the analysis that we've performed on it. But we also ran the same analysis for a number of solar farms of varying sizes, different voltage levels at the point of connection, different areas of the network at which they were connected, different topologies, different inverter manufacturers, all sorts of things. And ultimately, again, just very simple analysis of the actual detected impact or the estimated impact based on the analysis that was performed. And again, we see an increase around the 5th is generally the highest that we see, and this is for solar farm 1. You know, what is interesting to note here is that solar farm 1 is actually the smallest solar farm that was analysed. Apologies, that sort of information probably should have been provided in the slides themselves, but all the information is in the report as well, the final report. But we see this kind of tapering off of impacts, and again, we also see there at solar farm 3 site, we see some attenuation at the 7th and the 5th, and all other impacts are limited to quite a limited, I suppose, value based on the existing distortion. So moving on to the data that was analysed in the Netherlands. So there's the site. If anyone's interested, by all means, go and have a look. So what is actually available on that site is a whole heap of automated power quality reports. So not just harmonic distortion, but I believe unbalance, flicker, voltage levels, and a few other statistical factors. And what this allowed us to do was ultimately download all of the reports, which came in PDF form, unfortunately, but image processing was used to convert the PDF into numerical values, and trends were able to be actually developed based on the processed values. So as mentioned, the sites were identified based on available information of large offshore wind farms that were being connected to the network. And these sites were analysed and ultimately just the trends were defined. So what we see for the first site that was analysed, which was a substation in Eemshaven. So we see generally a few things, and the first is actual seasonal peaks and troughs. So what we see is the European summer, we tend to see a reduction in overall THD, or the trend of THD, and that seems to kind of pick up towards the end of the year, after which we kind of see these natural trends that occur. So I think in total about 4 sites were analysed. There was a lot more data available, but these were the ones that were identified in which there was enough data to analyse both pre and post connection of the wind farms. But these sorts of seasonal variations were common across all sites. But also interestingly is that we see this downward trend that occurs over a number of years, all the way up to the date of commissioning of this particular wind farm, which was in the order of a couple of 100 megawatts. It's quite large. And then we see ultimately the trend kind of flatten out. We still see those natural variations, but we see that downward trend kind of flattens out, and things kind of even themselves out, I guess. Looking at another site, West Meerdijk, again, we see these seasonal variations, but ultimately we see that the trend is kind of on a downwards slope through until the date of commissioning, at which it again flattens out. We've got about a year's worth of data missing, but we pick it up once the data is available again and see just kind of a very a much more smooth level of distortion that is occurring at that substation itself. So what does all of this mean? Well, again, it's very difficult to provide absolute statements, but some discussion was had with the Dutch TSO. We were not given any specifics, but simply there are a number of potential impacts that we may be visualizing here. One of those may be that increased cancellation. So we've got more harmonic sources that are connecting to the network, and these interact with each other and could ultimately bring down the overall distortion, including the passive componentry of individual installations may actually act as harmonic sinks for major harmonic orders. So that may be bringing down overall THD. Also, there is the potential that because the connections are so large, the requirement for the TSO to actually bolster the network at the point of connection or around the network of connection may actually be impacting the overall THD. So that would kind of go some way to describing that slow downward trend that kind of happens over a number of years, all the way up to commissioning of the installation itself. But the big outcome to this is that, well, we're not seeing this linear increase of harmonic distortion, even though we are seeing a substantial increase of harmonic sources being connected on the network. So that kind of lends to the fact that a revision of the harmonic management process overall is probably a good idea, just to make sure that what we are doing is robust, but also efficient. We're not over penalising, we're not over restricting or limiting connections based on harmonic distortion, and we're doing things in a more optimal manner rather than just brute force and assuming that everyone requires to mitigate their harmonic emissions. So I'll take a quick break there and open up to any questions that anyone may have. We'll double check the chat to see if anything's been posted. I can do.
Yes, we only have the one question, Jason, and I think the question is derived to the results that you just presented. The question is from Abdul saying, what was going down before in regards to harmonics? I assume we're talking about the harmonic levels.
By going down before these trends. Sorry.
So the
trend's going down before the green line. Yep. Oh, sorry. Yes. So that goes part of the way to, I guess, what I was describing before. Very possible. And again, we don't have any detailed information given to us. But one of the hypotheses is that in preparation of connection of a significant amount of renewable energy generation, the network needs to be strengthened to ensure that, well, not just harmonic distortion is being managed appropriately, but overall stability of the network itself is being managed. So that's one hypothesis. I'm sure that there's probably a few others that could be thought up fairly quickly. That was kind of what we came up with.
I've probably got time for one more question, I think. Yep. And this one's from Saboteur, or from, sorry, on my screen's scrolling, Sereniel Saboteur. So SF3 for the solar farms. Yep. Why is there a difference in the results for that graph? So in reference to SF3, I assume we're talking about the negative deflection. Yep. And has lower harmonic sources versus the other sources. Yep. So just a comment on that.
Yep. So again, very little detail with regards to specifics of the installation. So we can't say it's not that we can't say, we don't know whether or not harmonic mitigation was required by individual installations. We can't tell you if there was particular network augmentation that was incorporated. There's very little that we can say with any degree of certainty. But again, it's when comparing with the other installations, it's important to note that there is a wide range of variability between each of the individual installations. So it may be sheer dumb luck that the measurement period for solar farm 3 meant that it was excessively high during the pre-connection phase and excessively low through no fault of the solar farm itself, or there may be a level of interaction that is occurring. Given the substantial change, particularly at the 7th, we see about a change of 0.4% of the nominal voltage. That would suggest that there is some degree of harmonic sinking ultimately of the site, whether that be through, say, filtering or potentially even just the passive components, say the transformers, the collector network, actually acting as a harmonic current sink for that particular area. That's about all I can say.
Okay, I think we've got time. We might just address one more question and
Sure.
then carry the subsequent questions over to the next into the final period of the workshop. But so Joseph has got a question in regards to large installations making the harmonic distortion better, and he's just looking for a point of clarification, and I guess it's an opinion more so than anything. But does it mean that a few large VRE connections will make the harmonic distortion better, or many VRE connections that leads to a larger volume will potentially make it better?
It's all possible, I guess.
I guess one of the points that you did make during your presentation there, Jason, was that when there is a large volume of these connections, there is usually some infrastructure upgrades, which are either prior to or subsequent to that installation. So some of the results I know have been sort of linked to that, where there has been an infrastructure upgrade.
Yeah, I think that's a very real impact. And looking at, I mean, I did the review of the Dutch PQ data really was a lot of Googling, a lot of just kind of coming to understand how that network was conducting itself with this significant amount of offshore wind farms that were being connected. There were a lot of press releases, there were a lot of communiques that were submitted by the TSO itself that identified, without specifics, but identifying that particular upgrades were occurring in certain areas that aligned with where particular connections were being made, and those sorts of communications kind of lent to the fact that, or lent to the suggestion that this strengthening of the network could have a very real positive impact on the overall distortion itself. So yes, I guess is the one word answer.
Fantastic. All right. Look, thank you for those who have provided some additional questions. What we'll do is we'll carry those additional questions over to the end of the final session, but we'll let Jason continue on to the harmonic allocation section.
Thank you. Okay, so the next work package was really focusing on the methodologies used to limit harmonic distortion within the network. And so these ultimately are a handful of guiding principles, even though they do exist as standards. There is one in Australia that has been adopted as a standard, even though it has not achieved international standard status. But these are ultimately guides for NSPs to use when a large distorting installation is being connected to the network. Some processes that may be implemented so that a whole host of harmonic sources can be operating without distortion flying out of control on the network itself. So some of you may, or some I know, are very well understand these documents very well. But for those that perhaps maybe only understand them in an abstract manner, a critical review of international harmonic methodologies was conducted for this project. I read a lot of grid codes and electricity rules and guides and principles and all sorts of things. And ultimately what we found that we could break it all down into two very general categories. Good. Yep.
So how do we get rid of that?
I don't know. Are we okay?
I would just put the screen covered.
Okay.
Switch to the Teams screen as opposed to the presentations. Somehow.
It's being presented in Teams.
Can we just remove that?
I don't know how. No. We're gonna have to forge on.
Perfect.
There you go. Sorry, so we broke these down into two very general categories, and you see the titles that we gave them on the screen there. One being the fixed allocation methodologies, and one being network forecast methodologies. So these were ultimately given the titles based on the approach that was implemented, and we'll discuss that in a little bit more detail in a couple of minutes. But ultimately, what we can suggest with each of these methodologies is, well, with the fixed allocation, these sorts of processes will favour simplicity over technical rigour, I suppose. But what that requires is a whole host of assumptions being required to ensure that a wide range of network types are applicable. So for anyone adept in harmonic allocation, you'll be well aware of IEEE 519. So this is probably the most popular fixed allocation methodology that was reviewed. And we'll go through some of the details of that in a second. The other category that we defined was network forecast methodologies. So this is the most commonly used process in Australia and in Europe, and that's because it is based on the IEC technical report 61000.3.6. It's a very complex process, but it is also based on predictions or forecast of the final state of the network. And so what our studies found was that it is actually susceptible to uncertainty, which we'll talk about in a second. So firstly, the fixed allocation methodology. So like I say, IEEE 519 is a good example of this, but there are also different methodologies that are in use in France by RTE, the TSO in France, and also FinGrid in Finland has quite a different approach, but ultimately it all comes down to an allocation being received by a connecting customer based on the short circuit ratio of the installation, or to put it a different way, the agreed nominal power of the installation itself in ratio to the fault level of the network at the point of connection itself. And so the table on the right-hand side here is taken directly out of IEEE 519. And what you can see is that based on the ratio or the short circuit ratio of your installation, you will receive a harmonic current emission limit allocation across each harmonic order based on how strong the network is ultimately in ratio to the size of the connection itself. Very simple. That's all the information that you need to actually apply this process itself. And one thing I will note, it's not captured in. Actually, yes, it is. In the note below that table is that generators are actually restricted to the minimum allowable harmonic emission limit allocation, there's no good justifying argument for this, but ultimately what it shows is that generators are treated quite strictly under the IEEE 519 approach. As mentioned, the assumptions that feed into this sort of approach and fixed allocation methodologies make the process quite limiting. We reviewed the process on a number of Australian networks and looked at how the IEEE 519 approach actually performs. And what we find is that it is very limited in its capability, particularly in networks with any level of resonance or long feeders as well. It really starts to struggle, I suppose, and ultimately results in your planning levels being exceeded. So moving on to network forecast methodologies. So just a little bit of background. So the IEC 61000-3-6 apportions emission limits or emission current limits based on the size of the plant that is being connected, the location of the network, location on the network to which it is actually connecting, and also it builds in this final state of the network assumption. So to put it into an example, if we've got a network such as we have on the right hand side, a very simple radial network, which we've got a couple of long feeders, the NSP may make a couple of assumptions of where distorting loads may ultimately exist on the network itself. Using this assumption, it develops a harmonic allocation constant and will then calculate the allocated emission current limit to each connecting installation based on this assumption. Now, if this assumption is incorrect, it's very possible that the harmonic absorption capability of the network will not be adequately utilized. So what we can show is that it may result in planning levels being exceeded by a margin. In some cases, that margin can be quite large, or it can be significantly underutilized and your planning levels are only fractionally utilized, and resulting in an increased amount of harmonic mitigation that may be required, increasing costs to generators or customers, distorting customers in general, and ultimately resulting in an inefficient management process itself. So a couple of notes here is that sections of the standard or the IEC technical report is that prescriptive methodologies are very lacking in this document. It requires an engineering judgment to be applied. Along with that, a good understanding of the implications of the decisions and the assumptions that are being made is really important. But what we have seen in some cases is that the understanding and perhaps the use of engineering judgment may not always be present in the application. And ultimately, yeah, this identification that the sensitivity to uncertainty is a really important part of the outcomes of this project. So I won't labour the point too much because I kind of described it verbally in the previous slide. But when we talk about uncertainty, and keeping in mind that this document was developed again back in 1996, there has been an update in 2012, which hasn't been adopted by the NER. But the original, I mean, there's not a significant change in the overall process and the theory of the process itself. But, you know, 20, 30 years ago, assuming, you know, a very simple network and that loads were to come along and connect, or harmonic distorting sources may come along and exist within a network in a general way, maybe have been a very reasonable assumption to make. But what we're seeing more and more is that that assumption is no longer a very good one. And so we enter this period where the ultimate voltage levels, harmonic voltage levels, may significantly vary. And as I previously mentioned, it could be really heavily undershot or heavily overshot. We're kind of in this patch where we're really not too sure where things may actually end up. So in terms of the project, there was a number of different ways that we thought may be a reasonable way to manage this. These are still currently, I suppose, thought starters. They haven't been applied in anger, from as far as I'm aware anyway. But really just ideas as to how one might apply some buffer into the allocation process whilst still following the overall methodology of the IEC technical report. So I haven't gone into too much detail in these slides, but simply just presented as simple images. If you are interested, there are a number of publications that have been published and hopefully will be published, but also exist in the report, the ARENA report itself. One of the ideas was ultimately that we assume that there is a certain amount of generation that is to exist on a network. Beyond this amount, we see a falling probabilistic or falling probability of connections of renewable generation that may exist. And we can feed this into the remaining or the existing IEC methodology itself. Another process that was and is still being looked into is how we might actually look at networks with multiple long feeders, and how, firstly, identifying numerically the impact of uncertainty of both loads and generation, and providing a simple alternate method which minimizes the amount of ultimate eventuating scenarios that actually leads to planning levels being exceeded or significantly underutilized. So this process itself is still in development and still being considered. It's all based on, I suppose, statistical probability of the eventual state of the network itself. It's showing promise, but also I suppose the final point there, without increasing complexity, is certainly one of the challenges that needs to be addressed with this particular component. So there's still a bit of work that needs to be done in the area of allocation and assessing allocation methodologies. There are a number of emerging processes that are starting to gain traction. One of them is known colloquially as the headroom approach. That is ultimately looking at the distortion on the network and apportioning the remaining amount to future connections ultimately. This is currently written into the British allocation methodology, ER or engineering recommendation G5/5. I know it's also being applied in the Irish transmission network as well, AirGrid. But whilst it is currently being used, there's very little understanding of the actual implications. We are trying to build that level of experience. We are trying to understand it in a little bit more detail, exactly the challenges that need to be overcome, the advantages, and really the practical application, and how it is most efficiently utilised. There are also changes that have been written for the IEC technical report 61003.6, which is still being negotiated and discussed in appropriate working groups. So when those are eventually published, we'll be looking into really the ultimate impacts. So high-level outcomes, there are a number of allocation processes that are available worldwide. Fixed methods are suitable only for a limited number of network types, and what we found that here in Australia, it's actually quite limited. And the network forecast methodologies that are currently in use here in Australia, we've found can actually lead to increased distortion levels depending on particular assumptions that are being made. But it can also lead to conservative mitigation requirements and ultimately underutilise the power system absorption capability. So revised methods certainly are available, but need to be further discussed and looked at, and practical application certainly needs to be considered in further detail. And I'll break here again for more questions. Sorry.
All right. So there are a couple of questions. There's a couple of questions, a couple of comments really in the chat. So there's a comment here from Andrew Milne, which I assume refers to the fixed allocation type methodologies, the IEEE type way of doing things.
Yep.
And he says that at least it is current and compliance is not dependent on a changing harmonic impedance. I don't know if you've got any comments around that.
Look, I think, well, the issue of compliance, I think I wouldn't say is not dependent on an impedance, although I'm not too well aware of the compliance assessment process that is identified in that document. But yes, it is current. I think the most recent version was last year or this year. It's fairly recent anyway. But yes, absolutely. The outcomes of this project were not to say that fixed allocation methodologies are invalid and unusable everywhere, but they are limited in where they can be appropriately used. And what we found was that here in Australia, there are a lot of conditions in which they really weren't very suitable at all.
Question here from Umberto asking what the allocation for distribution networks to transmission connections are in Australia and whether or not there are filters at these connection points. There's a little bit of further commentary from a couple of other people in the chat with regard to that. So allocation for distribution networks, I think it's fair to say is fairly arbitrary, isn't it? And at the discretion of the TNSP in most cases is my experience.
Yes, yeah, I'd agree. There seems to be a bit of, well, kind of like you say, at the discretion of, whether that is fair or the intention of the processes themselves is probably up for discussion, I think, and probably a worthy discussion as well. And not just between TNSPs and DNSPs, but between two transmission networks as well, is something that is starting to become a little bit contentious, I think.
And with respect to filtering, again, my experience is that there isn't a lot of harmonic filtering at bulk supply points, if you like, or transmission substations. Our philosophy in Australia is generally that the customer is responsible for controlling the current through the IEC allocation process. And if they can't meet their allocation, the filter will be at the consumer premises.
Yes, yeah. In terms of harmonic filters at the intersection of a transmission and distribution network, I couldn't say a blanket statement that no, there are none. There very well may be, but generally speaking, like you say, it kind of seems to be managed further down in the system.
And this might be the last one for this little break that we have here. From Joseph, what is the general view of NSPs allocating harmonic voltage limits as low as 0.03%?
So there is a caveat, and I think I saw Umberto responded. 61,003.6 recommends a minimum allocation of 0.1%, which, yes, that does exist in the document itself. But what we're seeing, and this might be a little bit abstract, but what we're actually seeing is that there are a lot of connections that are occurring now, or a lot of connection requests that are receiving allocations of 0.1% across the board, which is kind of suggesting that, yes, this 0.1% minimum allocation is being used, but the process itself and the ultimate calculated allocation is suggesting that it should be ultimately lower. So kind of suggesting that the process may not be fit for purpose, or it's really heavily limiting ultimate connections. So it's an interesting kind of outcome that seems to be kind of happening more and more in the past couple of years. Just interesting.
Well, we might slip one more quick one in. Any chance that the 2001 edition of the standard is going to be updated in the NER anytime soon?
Very possible. And I think it really comes down to, well, I think a rule change request can be submitted by just about anyone. But one thing I'll note is that AEMO released a document. The title of it escapes me now, but it's something to do with technical requirements for connections. And ultimately, they've identified a number of things that need to be looked at to try to make the connection process a little bit more relevant and less of a blockade for connections to actually be made. Now, it doesn't state that specifically that harmonics are going to be addressed in the proposed work, which is yet to be undertaken, but it does identify that there are a number of out-of-date standards and documents and reports that are referenced in the NER. So it is possible that we may be seeing an update kind of being forced through by AEMO itself or interested parties if anyone wanted to submit a rule change request.
All right, we might continue on at that point then.
Yep, no worries. Okay, so we will move on to harmonic source aggregation. So I'm guessing that probably a number of attendees will be aware that ultimately harmonic source aggregation is a matter of assessing the diversity between two individual sources. So if we consider the graph on the right-hand side, we've got two current sources. Frequency can be whatever, whichever frequency, even the 50th, the 50 hertz. And so if we assess the harmonic current between customer 1 and customer 2, that flows through the collector feeder or the collecting cable that transports the current from the two customers, the phase angle between these two sources is 0, then we will see ultimately an arithmetic summation of these two current sources. So I1 plus I2 is equal to IT. Now, this is all well and good provided there is no phase angle diversity, but what we wanted to review using empirical data was whether or not once the frequency is no longer 50 hertz, so as we step up into harmonic orders, what is the level of diversity, phase angle diversity, that we may expect between two individual sources. Now, the graph here identifies customer 1 and customer 2, but what we were actually reviewing in this study is the emissions of identical harmonic sources. So in this case, it was actually individual wind turbine generators. So anyone familiar with 61003.6 will be aware of the alpha law or the summation law, and this ultimately attempts to build in some statistical diversity into the process itself, assuming that some degree of diversity exists between individual harmonic sources. However, most commonly in Australia, when undertaking harmonic emissions assessment, and I'm talking about pre-connection compliance assessment, we assume that there is no diversity between identical sources, which may be a fair assumption to make on the face of it. You know, you've got a whole heap of identical inverters, devices from the same manufacturer that are connected in close electrical area and close geographical area. You know, the generation sources that are connected on the DC side of these inverters generally exposed to very similar conditions. So you might be safe to assume that the harmonic sources are going to be somewhat similar and that the phase angle is going to be quite low. So we wanted to look at a particular set of data that we had, and specifically we looked at a large wind farm for which we had data a bit over 300 megawatts, can't remember exactly the size of it, but we had a whole heap of power quality monitors that were connected across the terminals of each individual generator. As you can see on the right hand side, these little red rings identify where each individual monitor was connected. So we were monitoring at the terminals of each individual generator and also at the collection or the aggregation of the generators themselves. Now this feeder diagram is actually just a representation of a single feeder within the installation. There were, I think, a total of 8 odd feeders within the installation. So it's not the entire installation itself, but it is a single feeder of the individual installation. The data that we were looking at spans a 10-day period in which the generator was allowed to operate just as it normally would. There were no special conditions, there were no limitations, there were no required operating conditions in which it was required to operate. We collected 10-minute average harmonic current magnitudes only, so we aren't looking at phase angles, we're simply looking at magnitudes. And also measurements below a measurement threshold were actually disregarded. So I'll go into this in a little bit more detail because it does have an important impact on the outcome. So what we can say is that, and kind of said it in the last slide, but I'll reiterate here, is that if there is very little change in the phase angle between each individual harmonic source, then ultimately the summation, the arithmetic summation of each individual measured current source should ultimately be very close to the value that we actually measured through that collector cable there. So just considering the measurement threshold, so we followed the IEC technical report 61000-4-7, in which we were able to identify what the minimum threshold for the for each individual measurement or PQ monitor was, and any measurements below that threshold were completely disregarded. And so it's important to note here that the measurement threshold for the individual generators is different to the measurement threshold for the collector group monitor itself. And so we actually have periods where we've got valid measurements for the individual generators, but invalid measurements for the collector group itself. We'll go into a little bit more detail in a second. So just noting there that there were a significant number of measurements. When I say significant number, I mean it is the vast majority of measurements were actually invalid or fell below the minimum measurement threshold across all harmonic orders for the collector group. And there are a number of harmonic orders, well, a lot of harmonic orders that actually do not register a single measurement above this measurement threshold. So entire harmonic orders were entirely dismissed just in this process. So there's a graph on the right-hand side that needs a little bit of explanation. So firstly, what it shows is the percentage of collector group measurements or the collector cable measurements that fall below the minimum measurement threshold, and that's represented by the blue bar. And so looking at this graph, what we can see is that, say, for the fourth order, we've got 100% of measurements that actually fall below the measurement threshold through the collector cable itself. So there is not one single measurement for the fourth order through that cable that was actually above that threshold. Same for the sixth, eighth, and so on and so on and so on. And the red bar shows the proportion of the proportion of measurements that fall below the collector cable threshold, for which the aggregation of the individual generated measurements actually exceed that minimum measurement threshold. So what I mean by that is that if we look at the fourth order again, we've got no measurements that exceed that, that measurement for the collector cable, but we've got roughly 57% of measurements from the individual generators that when we sum them actually exceed the minimum threshold through the collector group itself. So what this is saying, why this is important, is because for that 57% of measurements, there is a significant amount of diversity that's occurring. We can't say exactly what the level of diversity is because we don't have that a valid measurement for the collector group, but we can say that there is a significant amount of diversity that's occurring because the aggregation of the individual sources suggests that there should be a substantial amount of current that's going through that through the cable. So this will hopefully become a little bit more clear in a couple of slides. There's also a publication on this one as well if it's of interest to you. So just the number of measurements that are actually valid through the collector group, collector cable, across each harmonic order. For the first, obviously, it's going to be 100%. But for the second, we've only got 75% of measurements are actually valid. For the third, that goes to 76. But then as we go up in frequency, it falls off drastically. So for the fifth order, we only have 37% of overall measurements are actually valid through the collector cable. And it goes down as the frequency goes up. The reason why we stop at the 15th is because above the 15th, we have no valid measurements for any harmonic orders whatsoever through the cable. So those measurements were completely disregarded. So to look at the magnitude of error and to see how capable this summation or this assumption that there is no diversity between individual sources, first we validated the data and the analysis process itself by looking at the fundamental current. So what you can see on the left-hand side is we've got a scatter plot with the x-axis representing the measured current through the collector cable, and for the y-axis representing the aggregation of the individual measurements themselves. So if we have a lack of diversity between phases for each of the individual harmonic sources, we should ultimately get a straight line that passes through the data set, and that straight line should ultimately have a gradient of 1 and a x-intercept of 0 if the assumption was valid. Now we can see for the fundamental current that this is quite a good assumption, as we would assume, and now it also confirms that the process is appropriate to assess harmonic emissions themselves. So we've got on the right-hand side now the same scatter plot, but with a little bit more detail for the fifth order harmonic current. Now what we've got is, well, firstly, what we can say is that the points that exist above the black line, and the black line is the gradient equals 1, y-intercept equals 0 line. So this is if the assumption was correct, we should see our data set following this line. Now we've got a set of data that exists above and below this line. Points above the line suggest that the aggregation, or the assumption that phase angle is 0 between individual sources, actually overestimates the actual emissions, the measured emissions, which suggests that there is actually diversity that exists between the individual sources themselves. Now, there are also quite a number of points below the black line, which actually underestimate the actual emissions. Now, that suggests that there are harmonic sources that are present in the network or in the circuit that aren't actually captured by the individual generator monitors. Unfortunately, we don't have enough detail in the data to actually determine the source of this excess, but certainly an area for more thought, at least. So also in terms of this graph, we've got a high number of measurements in which the summation of the individual generator emissions actually exceed the minimum measurement threshold for the collector cable monitor, but which they don't actually exceed that current that flows through the collector cable. So those are the orange points there. And as shown in the previous slide, this accounts for, what was it? 63% of all measurements actually exist in that orange frame right there. And the remaining blue is the remaining 37% of valid emissions. So all of that is what I've just explained, but ultimately what we're seeing is that there is rarely a strong correlation between measured and calculated values. And this ultimately identifies that diversity is quite common, even at characteristic harmonic orders, such as the fifth. And this sort of analysis was performed across all harmonic orders, and particularly those with valid measurements. As you can see here for the 11th, we have every single measurement actually overestimates the assumption that, or the assumption that phase angle diversity is 0. So then we looked into the possible error or potential error that this sort of assumption can have. And what we can show is that assuming that there is no diversity between harmonic sources overestimates all measurements for harmonic orders 2, 11, and 13. And what we can see is that there are some underestimations, and that's what I was referring to previously, where there are some limited number of measurements that fall below that black line for the 3rd, 5th, and 7th. But we certainly need a little bit more data and a little bit more thinking around as to exactly where this is coming from. The maximum error that was detected was above 800%, kind of bordering on 900% for the 11th order. But also what we can see is that, generally speaking, as the frequency increases, other than the 7th, we see that the actual range of possible error increases quite substantially. And that's, well, reduced a little bit for the 13th, but we see this kind of, this general increase in range of possible error based on this sort of assumption. So some high-level outcomes. Ultimately, what we're seeing is that there is a significant amount of diversity between identical harmonic sources that are operating under very similar conditions. We also found that there were a limited number of harmonic orders that actually had measurements above the minimum threshold, making it difficult to actually determine the degree of diversity, but certainly identifying that diversity did exist. There is a significant amount of error that may be inserted into many processes based on this assumption. And this can ultimately increase the likelihood of mitigation and also impacts the way that processes such as compliance assessment are actually performed. And break there for any questions.
Okay, yes. I will go through a couple of these questions. So one of the first ones that I've got here, and this is, I think, probably relatively straightforward for you to answer, Jason, but this is a question from Stephen. So the aggregation methodology might be renewable energy generator type dependent. Wind farms are usually quite spread out with long internal networks, so higher impedance between individual sources, etc. So it's a good comment, Stephen. Solar farms are much less spread out and individual sources are electrically closer together. I suspect that the best approach is for the proponent to model their entire network. I guess Stephen's in its entirety, I guess, is what Stephen's suggestion, to work out their true aggregation rather than rely on summation laws and so on.
I think, well, just one comment to make there is that we did look into impacts of the passive components, so the cables impacting the ultimate aggregation of individual sources. We find it to be quite limited. And it's actually looking at the diversity of phase angles of the actual emission, the source of emission itself, to have the largest impact. But wholly agree that, well, what we would like to do is exactly that in a solar farm would be ideal, just to get start to build empirical experience in all sorts of renewable energy technologies.
Yes, and I guess the other aspect to that question would be that, you know, what information is available at time of the first instance when we're trying to work out an allocation.
Absolutely.
As opposed to that detail being available later on as the plant design progresses. So thanks for that question, Stephen. Another follow-up one from Stephen. Did the analysis that you presented, Jason, consider that the emissions of different harmonics vary with output levels of the inverters?
Sorry, can we go again?
So the harmonic emissions, they vary according to the output, the power output of the individual inverters?
Look, we couldn't find any, and this was done, I spent quite a bit of time trying to correlate emissions with active power levels, reactive power levels, voltage level, all sorts of things, and was unable to come up with a good correlation, I suppose, that was allowed us to provide any real kind of assumptions around overall impacts, because it would be a very useful relationship to have, so that we might be able to you know, have a good estimate as to what the worst case possible emissions may be, but particularly for wind turbine generators, we were unable to really find that correlation. Again, solar farms, I suspect, are a little bit different in that sense, and there may be a stronger correlation there.
I think just in addition to that, so from the point of view of did the analysis consider the different harmonic levels, although it wasn't shown on the slides purely from a time dependency point of view, that is, and I think it was over the period of about two weeks, that data that we're
10
using.
days.
10 days.
Yep.
So we did actually look at how the harmonics were varying over, you know, each 24-hour period as well. Jason sort of responded in regards to a direct correlation to output levels, but we've certainly considered it, bearing in mind that with the summation law, it's not just trying to work out a phase diversity, but it's also trying to work out a time-dependent diversity as the piece of equipment, in this case renewable energy generators, operate through that whole period as well. So, but it's a good point that you make, Stephen, so thank you very much for that. The last one, I think, is just a point of clarification from Umberto. So Umberto mentions that using the arithmetic summation law, exponent makes a difference for exponent equal to 2, so alpha equal to 2, in the contributed distortion of square root of the number of inverters. So if you have 50 inverters, the choice of arithmetic or summation law makes a difference of up to 7 times in the contribution. And he's sort of making that point in reference to trying to design a filter to cater for that level of difference. So just a general comment in that regard.
Look, no, it all kind of feeds into this. Well, something that we're going to be proposing as potential future work is how this feeds into the decisions that are made at the pre-connection state. So when we're developing these models and when we're assuming or not assuming diversity, it all has a very direct impact on very real decisions and decisions that ultimately may cost a lot of money. So yeah, a good point, and something that I think we need to be a little bit better at, I would say, and build experience in, rather than just blindly following, say a 30-year-old assumption based on a couple of measurements.
Thanks for that. A question from Richard is, what impact does the background in the network have on the aggregation analysis that we've done in this particular section?
Yeah.
So he mentions also that the background dominates inverter, well, background domination versus inverter emission domination. So did we consider that?
Look, we did look at background levels and how the actual voltage levels impacted the emissions. I think now we're going back about 12, 16 months or something. But from memory, it was because we did have the timestamps emissions for every generator and the collector itself. We were able to identify the domination of the individual generators themselves. I'd have to go back through and really reconvince myself of what I'm saying now. But there was certainly a consideration of background levels that was considered. I can say that.
A slightly less controversial one than perhaps then is how and where did you measure the harmonic current, noting that the background harmonic current will also have an impact?
Yeah, so just jump back so I can talk to it a little bit. So this bus that we can see at the top here is a collector bus that had a number of different feeders connected to it. The individual monitors, now what's not shown here are the step-up transformers for each of the individual generators. So these monitors existed on the LV side of those transformers. So we had to scale the currents down to the increased voltage of the collector network itself. And this was taken right at the bus bar, so at the far end of the collector feeder itself. Okay,
Thank you very much for that, Jason. There doesn't seem to be any more questions for this particular section. So thank you to Joseph, Richard, Umberto and Stephen for those questions this time around. We'll move on to the next section of the report.
Okay, so this is the fairly certain it's the final section that I'll be presenting on, and it is to do with harmonic mitigation. So zooming out a little bit and now looking at the a simple network as a whole. If we think about the fundamental philosophy of the IEC harmonic management methodology, in networks in which we've got sufficiently long feeders or in highly meshed networks, transmission networks, ultimately what the process is trying to do is to manage the harmonic voltage distortion levels at a particular point in the network. Now, because there is such variation of harmonic impedance across long feeders, what we can show is that your network will not reach your planning levels in a uniform manner. Or to put it in kind of an example form, for a network like we've got here, we will reach the planning levels at a particular point, and provided that we reach them at a particular point in the network, then we can safely assume that the planning levels across the network are all falling below the planning levels. Now, in this example, we have a couple of long feeders, and now these feeders are long enough to for charging line capacitance to have an impact. And so what we see is that we can actually have points of the network where our harmonic impedance is the highest, not at the very end of the individual feeder itself. And so that's all due to RLC components interacting and creating resonances that exist within the network. And so those are really the points at which you're expected to reach your planning levels first. Now, the reason why this is important is because at the moment, the methodology that is applied requires that harmonic mitigation to be applied at the point of connection for individual generators, as Sean mentioned previously in response to some of the questions. And so what this does is ultimately provides a low impedance path for harmonic current to flow to stop that current from flowing out into the network, hitting a large impedance and creating an amplification of harmonic voltage. So theoretically and fundamentally, this all kind of works out. It makes sense. But what we're seeing is in practical application, there are particular complexities that perhaps aren't being really thought about in too much detail. One of the complexities is that the connection of harmonic filters and passive filters, even just reactive components to the network, will ultimately change the harmonic impedance of the network. So not only can it shift resonant frequencies throughout the network and change the harmonic impedance of the network ultimately, but it can also have an impact on the expected emissions of an individual installation itself. So an installation may come along and connect and have its filter designed and everything's fine. And then 6 months later, another one comes along with another harmonic filter. And all of a sudden, the impedance that this connection sees is different. This filter becomes less capable to sink the harmonic emissions. It becomes less of a low impedance path, and ultimately things start to impact on each other. So there's this overall complexity that is not adequately thought about in our experience. And so really what is trying to be done is to manage the current emissions to ensure that the point of the network with the highest impedance reaches its planning levels once everything is connected. So we thought about this in perhaps a different way. I've got 3 examples given, one with a very simple transmission system, one with a distribution system with long feeders, a radial distribution system, in which there is resonance that exists. There's also I won't say a real world example, but it used a large sub-transmission system that was provided to us from an NSP and used harmonic modeling from manufacturers. So the first example, we've got a simple 4-bus transmission system with 2 upstream bulk supply points or sources, whatever you want to call them. We have a number of large distorting connections that are going to be connecting. And so in this example, we follow the Australian standards and we allocate emission limits for each of the connections. And ultimately that defines the limits, the harmonic current limit that is allowed to flow into the network from each of those individual installations. And ultimately, we will look at where the voltage distortion at the point at which the planning levels are expected to be exceeded or to reach initially. So in this example, we've got 4 equally sized generators that are connecting to each of the individual terminals. Each are allocated an emission limit. And what we find through through modeling is that customers connected to terminals 2 and 4 are emitting harmonic currents that are 20% above their allocated emission limit. So in this case, we can expect that our planning levels are going to be exceeded here at T3. terminal 3. So some level of mitigation is to be required. First, we look at the filters that will be connected at the PCC of the offending plant, so at T3, T2 and T4. And then we'll look at a scenario in which we connect the filter directly to the point at which the cleaning levels or the voltage distortion levels are the highest. And if we compare the two, what we see is that the size of the filter for the connection at T2 will be required to be about 730 kVAR. The size of the filter for the connection at T4 is about 120 kVAR. Now, if these connections are made, we've got an aggregate filter size of 850 kVAR, but what we see is that we reach our planning levels at T3, everything's fine. The customers are meeting their allocated emission limits and everything works out. If instead we connect directly a filter directly to the terminal at which the impedance is the highest, we see that the overall filter size is reduced by about 40%, which is not an insignificant amount, considering that what we're looking at here is a condition in which the filters considered are for a single harmonic order. So they're single tuned filters. This is generally not what would be used, but it gives us a really easy design process that we can compare and benchmark against. And so what we would actually expect is that the efficiencies would actually be somewhat higher in real world conditions. Moving on to the second example, in which we've got a distribution system, which we've seen a few times now, with a number of long feeders, generators are connecting throughout the network. We find ultimately if we use commonly applied modeling and data from inverter manufacturers, we find that all generators to be non-compliant. We find that all generators require a level of mitigation and that the network will exceed its planning levels. Now, point two on these two dot points here is really aligns with the experience that is actually being seen throughout the industry at the moment. We're finding that with existing processes, really it is very, very common for mitigation to be required for renewable energy generators. So this really kind of provides us a good space to kind of look at these impacts a little bit more. So if we follow business as usual and connected a harmonic filter to the PCC of each of the generator connections, limiting the harmonic current that flowed into the network and manage the harmonic voltage distortion within the network, what we find is that if we sum all of the ratings of the filters together, we've got about 760 kVAR of filtering that's spread out across the network itself. If instead, again, we go to the point of the network at which the planning levels are expected to be exceeded without any mitigation, size of the filter bottoms out to about 20 kVAR. So this filter is about 2.5% of the business as usual methodology. And really this efficiency is seen because the current emissions are aligning with a resonance in the network itself. So managing those resonances at the point of resonance is where real efficiencies can be made using this process. And also just to note that because we don't have filters scattered across the network, we ultimately reduce the impact that the filtering actually has on other harmonic orders, which we'd actually see if we use kind of the business as usual. So just a few notes there about comparing the existing and the proposed methodology. But what I suppose the highlight here is this relation of using the proposed methodology. The size of the filtering can actually be shown to be a fraction of the required filter if the filter is connected away from the point of resonance on the network. And that is not an estimate, that's not a rough guide, that's an exact value. It mathematically kind of works out that way, that to achieve the same impact, filtering external to the point of resonance, or to the external to the point at which the impedance is the highest, you require a much larger filter, ultimately, is what that's saying. Looking very, very briefly at the final example, we've got a network model that was provided to us from an NSP here in Australia. We looked at kind of different areas of the network, and now we split it up into particular areas, and we made connections, theoretical connections that spread across the network, and we focused kind of a lot of connection at strong points, a limited amount at normal or relatively normal strength parts of the network, and limited the amount of connections that were actually occurring at the weak points of the network. So what this shows, and it was all done in kind of stages. So we did it in kind of 500 MVA stages, in which we had a slew of connections that were occurring across all parts of the network. So what we're looking at here are the results of stage one. So we've got generators highlighted by these green kind of splodges, and firstly, what we see is that without any mitigation, without any filtering, what we see is that we hit a point of non-compliance that is actually 200 kilometres away from, electrically, 200 kilometres of line between the point of non-compliance and the nearest generator, which is actually this point here. And now this is the point at which our harmonic voltages are the worst. And elsewhere and upstream from this point, actually voltage levels are sufficient, they're fine, not an issue whatsoever. So looking at potential ways to mitigate this, these levels, we found that the quickest, easiest and simplest way was to actually just detune the upstream capacitor banks. So we were able to do that quite quickly, and then move on to stage two and applied another 500 MVA of connections, all with harmonic sources, punching harmonic current into the network. Again, same area of non-compliance. So this was the point at which the harmonic impedance was the highest for a number of harmonic orders. And what we find is that all we need is a 50 kVAR filter at that point, connected directly to that point of non-compliance. Now, if we compare that to that kind of filter size to what we're seeing being connected directly to PCCs of generators at the moment, we're seeing, filters that are 10, 20% the size of the nominal power of the actual generator itself, even to the point where the generator is no longer able to actually meet its reactive power capability. So the relative size of, when we start talking about tens of kVARs, is substantially lower. So what we found, and there's a full report or a full discussion in the report itself, but ultimately we just kept connecting large generation to this network, which was ultimately had quite a lot of weak areas. But we had 4 gigawatts of generation that was connected with roughly 23 MVAR of reactive filtering that was required. A number of reasons for this, but ultimately what we can show is that the filtering at the weaker points of the network, the size of the filter needs to be much smaller, because it has a much larger impact on the harmonic impedance of the network itself. All those other points I think we've kind of hit on. So this is something that we're looking into with great interest, and trying to socialise this idea with a little bit more vigour, and hopefully extending the experiences, the practical experiences, as best we can. because it's suggesting at the moment that real efficiencies may be made with a revised approach to how we actually approach mitigation in the network. There is certainly still a lot of experience and work that needs to go into understanding this as best we can. One thought, of course, is how we actually apportion responsibility and costs for mitigation. There are some thoughts around this, but certainly we just need to gain experience and have more discussion in that area. So I'll pause here for the final time for myself for any questions that have come in through the chat.
So thank you very much for that, Jason. There are certainly some questions here. Some of them we might have to carry over into Sean's section just because of topic area, but perhaps I'll let Sean dictate whether that's the case or not. So first question is from Andrew Milne. So thank you, Andrew. So for a generator, harmonic emission limits are defined as harmonic voltages at the limits of the point of connection. Hence, Andrew's previous comment regarding having harmonic current emission limits being more appropriate. It would also mean that compliance would have issues relating to your comment on having system harmonic impedances changing due to other network or nearby generator load modifications. So his comment is that we are finding that filters have been designed to sync system harmonics as well as in order for the proponent to be compliant. So do we have a general comment perhaps from Jason in the first instance, but maybe Sean as a follow-up?
Look, I think the use of voltage limits and current limits, I'm not convinced ultimately solves the problem, because really the reliance on network impedance and interaction between network and customer impedance having an ultimate impact on not just your current emissions, but also the impact that you have on the voltage itself. There are a lot of moving parts here it's nailing jelly to the wall, really, and trying to hammer home compliance on one rather than the other, I think, doesn't really kind of get us out of the woods, in my opinion. I think there's probably a lot that can be said and will be raised during the discussion session, so I might just leave it there.
Putting Sean on the spot, anything to add? Or
not strongly, no, other than to say, and this will come up when I speak in a little while, none of this stuff is very prescriptive at the moment, and there's various different ways that people are approaching this. What I believe we need is prescriptive methodologies that everybody understands, knows how to apply, and that's the path forward to my mind.
Thank you, Sean. And I think Stephen Sanini, who's online as well, has added to this discussion as well. And I think we will definitely address it. But Stephen says, yes, there are two components to harmonic impact: direct emissions from the plant, obviously, and the harmonic interactions with the network. And he gives the example of possibly at night when solar inverters are not operating. So it's significantly dependent on network impedance. So agree with that, Stephen. I think there is a possibility for shared responsibility here, and I think that's some of the work that Jason's alluding to, is some shared responsibility in managing those two interactions, of course. So which is a leading comment into the next question from Joseph. Would you suggest harmonic mitigation to be managed by the NSP at the PCC instead of the individual generators based on the study outcome? And there's already some comments on the chat in this regard, but I'll go with your initial response to that, Jason.
Well, mine would be, I think harmonic mitigation, harmonic management, I am of the strong opinion that it should be an NSP-led charge. And that is really because the level of data that is required and the detail of data that is required is generally not directly available to proponents or to the supporting engineer to proponents. And so quite often decisions are made on incomplete data sets, whereas someone with a full view of the network and perhaps even a view of distortion levels that exist, and also future changes to the network that may exist, certainly would provide vital information when determining appropriate, not just design of filters, but also location as well, in my opinion.
Thanks for that. And I think while there is some additional discussion on the chat as well, I think one of the points that that Stephen has raised in response to that, so the complexity in this, dare I use the term socialist approach to harmonic allocation.
I'll be a socialist.
The complexity is potentially economic.
Yes.
So would you agree with that? I
Yep.
think you just did.
Yep.
The technical solution is less complex in this approach. So
Agreed.
Stephen says that's good, but financially this is obviously much more complex.
Yeah, agreed. But I don't think it's insurmountable. It's something that I'm not marginally, but something I am in conversation with a few people with. I'd be interested to kind of hear any ideas to that degree as to how we apportion costs and responsibility. But certainly it's a matter of I think starting simple and increasing complexity as experiences are gained, I think, in my view.
Yep, and Joanne makes I guess a comment that complements that discussion in that Stephen initially said that managing harmonics from a network service provider point of view essentially shrinks these polygons that we're all doing at the moment. And Joanne has mentioned that the new system strength rule, I guess, does take that approach
that's
from the
right.
NSPs, and so perhaps there is a potential model for us to adopt that. So thanks very much for those comments. Right, we're running almost on time, a little bit behind, but perhaps we've spent more time on questions, which is great, than what we expected to. So given that we've been talking for about 2 hours now, what we might do is we'll take a short 10-minute break and come back and begin Sean's presentation. So my clock at the moment says 10:52. So if we could, we'll just let everyone take a 10-minute break, and if you could rejoin us, perhaps at 11:02, we'll aim for that. Perhaps if you could be back at your seat at 11, and we'll try and kick off once everyone joins us. Shortly after that is probably the easiest way to manage it, and then we'll hear from Sean. So thank you very much for your presentation, Jason, and hopefully see you all back in around about 10 minutes. Thank you very much. Okay, welcome back, everybody. Hopefully everyone had a chance to stand up, stretch, grab a refreshment and renew the energy levels to keep going. So as I mentioned before the break, we are going to hand over to Sean to present section 6 of the contents, the preliminary review of compliance assessment. So I will hand over directly to Sean.
Thank you, Dwayne, and good morning, everybody. So, as you've seen this morning, the main focus of this project was on the allocation process, but there was a small component related to a preliminary evaluation of challenges related to compliance assessment. So, what we were trying to do was understand the challenges, but there certainly wasn't scope within this relatively small project to solve them. So in terms of compliance, and we've sort of seen a lot in the chat and a little bit of conversation about compliance already this morning, we can think of compliance as pre-connection compliance assessment. So I apologise, there's an error on that slide. It should be pre-connection and post-connection as opposed to pre-compliance and post-compliance. But so we thought about these two aspects, you know, what we do before we're connecting a plant, and then what happens afterwards. As I touched on, I would consider the present standards to be far from prescriptive with respect to either of these compliance aspects, either pre or post compliance assessment, connection compliance assessment. So what we've observed happening is that NSPs are generally applying engineering judgment with respect to how we go about assessing compliance. So what that's resulted in is not necessarily consistent methods being imposed across the country, and you know, basically different ways of doing things. So just in terms of an infographic, this is basically an infographic showing the simple connection process, I suppose. We have an application, then the NSP will use some sort of methodology to give an allocation. In Australia, most of the time it's the 61036 method. Up until recently in Victoria, that wasn't the case though. They were using a more of an IEEE type method to do things. Once we have an allocation, we then go through a pre-connection compliance assessment methodology. This is sometimes termed the R1 way of doing things. And what that basically requires is modelling undertaken to verify if the plant can meet emission allocations. So this is the computer modelling side of things. Once that's done and everything looks good, we go ahead with connection and commissioning. Obviously, there's some commissioning compliance assessment work done during the R2 type testing. That wasn't really considered part of the scope of work here because it's I guess you could say it's just a short-term thing that's happening there. Then we have our post-connection compliance assessment, so ongoing assessment of compliance through field measurements. So for this particular component of the project, we were really thinking about those aspects in the red boxes seen on this slide here. So what are the challenges that we identified in relation to compliance assessment? One is that we're seeing a lot of investment in harmonic filtering. So the way that we're doing compliance assessment at the moment is resulting in many harmonic filters being required for plants. There's a big question mark over whether or not all of those filters are actually needed. There have been instances where plants with filters have been switched on and it's been found that the harmonic levels have actually gone down. A harmonic filter might not have been necessary in the first place. As we've seen from some of Jason's work in the previous little part of this presentation, filters at plants might not be the best way of doing things anyway. We've observed delays in connection and commissioning while compliance assessments are sorted out. There's often a bit of to and fro between the NSPs and the proponents about, you know, what compliance assessment does and doesn't mean, and how it should be worked out. Again, generally because of the lack of a prescriptive way of doing things. Less often observed, but certainly there have been instances of marginal projects being abandoned because of a need for filtering. Again, that comes from the way, in some cases, that's because of the way that we're doing our compliance assessment. What can't be argued is there's many studies that are being done to look at compliance assessment. Those studies sometimes go back and forth. Certainly with our work here at the university, we've repeated a number of studies because of things that have changed. Obviously that's a cost to proponents, it's a cost to NSPs, ultimately it's a cost to consumers. I think it's fair to say that most, if not all parties, and when I say parties, I mean both proponents and network operators, generally agree that the present way of doing things can be improved. In terms of the specific issues identified, I've color-coded this particular slide. Blue are pre-connection compliance issues that have turned up, and green are the post-connection compliance assessment issues that we've identified. In terms of pre-connection, number one is determination of appropriate network impedance, and there's been some conversations around that already. Many NSPs are now requiring the use of polygons, and well, whether or not we think that's the right way is a little uncertain. How we model the renewable energy plant remains uncertain, and the sensitivity of that plant to prevailing network conditions, whether that be impedance or background harmonic distortion in the voltage, is another issue that has come up. There's uncertainty there. How we go about application of stage 3 assessment in 61003-6. So, by what mechanisms can we potentially allow plant to connect and see what might happen? I think that's less of a technical issue and maybe more of a regulatory issue or a connection framework type issue. From the post-connection compliance assessment type area, two issues identified there. One is how we go about actually assessing compliance using field measurements. So we've talked a little bit about, compliance is, emissions are given as a voltage. We're generally measuring currents. The standard also requires us to try and evaluate plants in isolation, i.e. with a sinusoidal supply voltage waveform. So we know that that's not what happens when we go and measure field data. And there is no prescriptive way to really assess compliance based on field data at the moment. And then there's the issues around instrument and transducer accuracy, which again, we've touched on this morning already. So the outcome basically of this component of the work is that compliance assessment is definitely a challenge for both proponents and network operators. And we've identified a number of issues for both the pre and post connection compliance assessment. There's definitely appetite for further work in this subject area, and that leads me into the next part of my presentation, which are our next steps. So just before I do launch into next steps, one of the things that we are looking at doing that's not included in the next few slides is more in the way of this network-centric or network-led harmonic mitigation. So if there are people out there that are interested in that type of work, I'd encourage you please to just contact us. It's not sort of part of, again, what we're planning to do in the next part of this work, but it's something that we're doing separately and on the side. So please contact us if you're interested in that. So what we're doing at the moment is we're working with a range of stakeholders to develop a project that is seeking to provide prescriptive methodologies for compliance assessment. ARENA is supportive of this work into the future. I think ARENA, it'd be reasonably fair to say, have been fairly happy with the outcomes of the previous work and understand that management of harmonics is an issue related to renewable energy connections, and again, generally supportive of doing more in this area. We've developed a number of work packages generated from the project that we're talking about today. Three, I guess, areas of work that we'd like to look at: pre-connection assessment, post-connection assessment, and then some work looking at the compatibility or the planning limits. And I'm going to sort of touch on each of these in the next few slides. So with respect to pre-connection compliance assessment, we would like to look at how we model the network and the plant. We know that there's no prescriptive methodology for doing this at the moment, and the key challenges that we would like to address are how we represent the network impedance. So we know that at the moment there's a lot of use of polygons. I believe that there are a lot of question marks about the way that we do polygons. Because we've got fancy computer software when modeling, many thousands of network scenarios, and then we're generally taking some sort of the worst case scenario. In some cases, we take the 95th percentile type impedances. I think any of those methods is fraught with danger. And I'd really like to think that maybe we can do the polygons a bit better, certainly better in so much as reflecting more network operating scenarios that are more relevant to just this sort of broad brush approach that we have at the moment. We'd like to look at how we represent the plant in our modelling. So I think we'd all agree that the way that we do the plant at the moment, again, is open to some question marks. We've certainly seen situations where, multiple harmonic emission spectra for the same plant. How does that come about? I think there's big question marks around the way that the emissions are actually worked out in laboratory, and it certainly doesn't take into account any of the network operating scenarios that might be relevant. And I think there's a big challenge around how we apply the Australian standard and whether it remains applicable in this subject matter area. So we know 3.6 is a technical report. It hasn't achieved international consensus. We also know that it wasn't designed for use in mesh transmission networks, yet it's still being applied in that way. So I think there's big question marks around what we can do with 3.6 to try and make it more applicable for these renewable energy connections in transmission networks, and to a certain extent even in weaker sort of sub-transmission networks, 22 kV and that sort of thing. In terms of post-connection compliance assessment, we know that obviously that uses monitored data to try and assess the plant compliance. The challenges here are how we actually determine the customer contribution. As I've sort of mentioned, that is influenced by the network impedance and the network background distortion. So how do we separate out what a plant is actually doing compared to what's coming from the network or the network's contribution to that? So we need an appropriate assessment methodology to do that. There also needs, I believe, to be some prescriptive information or guidance around accuracy of instrumentation and transducers. We've done quite a bit of full rated voltage frequency response testing of VTs here at the university. And the upshot of that is there is no way that these VTs are suitable for measuring high order harmonics. So what are we going to do about that? Final part of the project that we're sort of working on at the moment is a review of harmonic limits. So I'm not sure, it's probably not news to anybody on this presentation that harmonic voltage limits decrease as the order increases. I don't believe there's any strong technical reason why that should be so. So what we're trying to do here is seeking to understand if there's scope to vary these limits. You might know that the IEEE don't have a harmonic voltage limit profile that looks like this. They have flat limits out to the 50th order and considerably higher voltage limits as well. Before we do go sort of suggesting anything radical like varying these limits, we need to understand the implications on equipment. So this part of the project would involve quite a lot of laboratory testing just to understand the immunity or the susceptibility of equipment connected to the network. Obviously, if we're able to vary these harmonic limits, it gives more headroom with respect to emissions for connections and potentially solve some of the compliance issues that exist. So just to sum up, basically our, I guess, aims for this project, or this next steps, if you like, is to develop a pre and post connection harmonic compliance assessment process that's holistic, robust, prescriptive, and consistent. And once we do that, we'd be seeking to influence in some way the Australian standards, and through that Australian standards, the national electricity rules. Whether that is a change to the standards or it manifests itself as something like an E&A guidebook, that's a little uncertain at the moment, but certainly something written that can be referred to by the industry that describes a process that's consistent, I think would be a very good thing for the industry. So that brings me to the end of that small sort of bit about compliance. I'll hand back over to Dwayne.
Yes, well, we just recognise a few comments in the chat for the moment. So following on from Jason's previous session, just in regards to system strength, we've had some comments around, you know, do we combine power quality into the same sort of bucket as system strength, and some arguments for and against that on the chat existing. And I think the original comment was probably just to have a similar process to what's being applied to system strength. So I think we can probably discuss that further as we move into the open session. The other thing that Stephen has mentioned in the chat in regards to Polygon is that a level of certainty, or I guess the percentile of each dot point within the polygon needs to be considered as well, to make sure that system normal states aren't excluded in the simplification of that process. And I agree wholeheartedly with that particular comment, Stephen. The question is, how do we determine those scenarios? Well, we can determine them, but
just to add to that, 100%, Stephen. We've certainly seen instances here with work that we've done where the system normal state has been excluded through a 95th percentile type, you know, basically throw away 5% of the impedances. What I believe is a little frustrating around all of these polygons is that in some cases the network operator is not very forthcoming about what the more likely operating scenarios are. I think it'd be good. I mean, I'm happy to be corrected by network operators who are on this call, but I believe that there aren't a huge number of normal operating states for the network. We talk about 95th percentiles a lot in power quality. I don't believe that there would be many operating scenarios that the network is sort of operating at for 95% of the time. It's probably only a handful. So I think there needs to be a little bit more information sharing as to what those operating scenarios are, and they should be identified somehow on the polygon, whether it's a different color or some other way of doing it. Because at the moment, all of those red dots on that polygon that I had on that slide mean the same thing. And some of them are probably only going to be there in, you know, the very worst case scenarios.
Okay, fantastic. Thanks for those comments, both online and from Jason and Sean. I'm just going to hand back over to Jason to just run through the conclusions of the existing project. And Sean's obviously already talked about some of the work that we have planned for the next stage of this project. And then once we've gone through the conclusions, I think we'll open up to the open session.
Let's get you to control slides, Sean.
Yes.
Just jump one.
Yep.
Okay. So really just a very, very, very high level conclusion of the project after 24 odd months worked, 18 months, can't quite remember. So really, well, jumping all the way back to the start, looking at harmonic trends at the moment, we're certainly not seeing this linear increase or significant increase in harmonic distortion, even though we are significantly increasing the number of harmonic sources in our network. In fact, there are even some studies that were pulled upon that found in some levels within Australia that THD levels are actually going down in recent years. Now, this is something that, whilst it may be what the data is telling us at the moment, may not always be the case, and what is true today may not be true tomorrow. So keeping a close eye on these sorts of trends would certainly be of benefit, and particularly focusing on areas where we expect large installations to be connecting, and particularly keeping an eye on areas where we might be losing a substantial amount of synchronous generation or synchronous machines. Moving on to harmonic allocation, the processes, as discussed, are quite limited in what they are capable of doing, and the complexity and the detail that is required, particularly within the Australian standard process, certainly is, well, can be heavily impacted by such things as uncertainty, managing conditions of resonances and networks, highly meshed networks and networks with long feeders can be a particular challenge. Some preliminary revisions have been provided, although not discussed in great detail today. Those sorts of things are available in online publications and also the final report. But ultimately, some more work is necessary. Really, we want to see some practical steps being applied to look at how we might actually better manage the overall distortion and the allocation of emission limits to individual customers, and ultimately how we assess that compliance, although that comes in a couple of sections' time. Looking at source aggregation, of course, there was a significant amount of diversity that was occurring between harmonic sources that we found based on measurements that we had. And this sort of diversity and these sorts of interactions has a very high impact on the way that we model individual harmonic sources, and ultimately how we perform compliance assessment and even allocation. So it's something that requires a little bit more thought. And certainly a lot more data would be very useful in this area. Mitigation, a revised process was presented in terms of harmonic mitigation, in which we found that filter sizing may be optimized through management of harmonic impedance rather than harmonic current. And that ultimately allows for a much simpler, cleaner process that is capable of being implemented by the NSP, although, as we've already discussed and probably will discuss in a few moments' time, requires a little bit more thought and a little bit of discussion as well. Compliance assessment, as Sean has identified, the existing practices, what we're seeing is increasing the likelihood of mitigation being necessary. This kind of exists across the whole gamut of studies that are required through compliance assessment, both pre and post connection. And really, some of the high impact factors that we have identified is the harmonic model representation of inverter-based resources, and also the network are really, really important, but also the lack of prescriptive methodologies that actually exist in standards and guiding documents is certainly having a big impact on the overall outcome of what we're seeing at the moment. So we are advanced in an advanced state of developing a future project. We are hoping that this is something that we can ultimately undertake. Firstly, looking at pre-connection compliance assessment processes, so ultimately harmonic modelling, how we assess harmonics before an installation is built and only in the design process, and checking off some of those high impact factors that I previously mentioned, such as the representation of the inverter-based resources and the network. Also, review of the definitions, methodologies, and measurement processes in post-connection compliance assessment. I think there's even been some comments in the chat regarding really the difficulties and some of the challenges in this area. So providing some very real and very practical processes would certainly be a significant improvement. And also a review of the planning levels. So the existing levels that have been defined lack justification, really, in our view. And a review of the implications for the connected equipment is proposed, so that we may look at how we may better actually manage distortion levels and assign planning levels throughout a network. I'll just go back. Done that. Yep, and that is it.
Fantastic. Do you want to take it out of prison?
I can't.
No, you got it. All right. Well, thank you very much for that, Jason. So, so we're going to have an open session now, and I think we might start the open session. I'm going to hand over to Sean to try and coordinate the logistics of who gets to talk and when. So what I'm going to do is ask people if they can to perhaps raise their hands just using the reactions.
Yep.
And we will then hand over so that you can speak verbally. I know that there's some really good comments about concern, so maybe we'll use this as a leading, just while people are contemplating their questions or comments overall, either on the project, on the second stage of the project, or perhaps just about harmonic issues, either from a network or proponent point of view. We'd love to hear just your comments if you don't have questions as such. But one of the things that Joseph has highlighted to start with, and perhaps I'll get a response from Jason in this regards, just to kick off the open session, and then let the raised hands dictate where we go to from there. So Joseph says, what is the opinion of harmonic compliance of plants in the future? And there will be more transmission lines. Agree, Joseph. More line charging capacitance. Agreed. Fewer synchronous generators as harmonic sinks. Agree with all these complexities. Will the existing plants which are compliant at present be non-compliant in the future? And if so, who's going to be responsible? Over to you, Jason. A nice, easy one to start with.
Yeah, all really good points. And yes, agree with Dwayne and agree with yourself. All really good points. Something that I don't think is really very well captured in the existing documents in terms of, I mean, we've been speaking about lack of prescriptive methodologies and robust methodologies and processes, and this is kind of one of those ambiguities that currently exist. Really, it's down to the NSP to determine what is important and what is not. And so if ultimately a transmission or a network augmentation comes along, let's look at, you know, things like a res being connected or something like that wasn't even dreamt of 20 years ago. All of a sudden, transmission system looks very different. And what you might find is that what was once compliant is no longer. Yes, this is all very possible. We can't say absolutely for every generator, but very, very possible, as you've identified. Who will be responsible? Well, that all comes down to, I guess, really the cause of the change, the interpretation of the rules, and who's holding the sword at the time, I guess. As to where it falls, but I mean, I think that there might be probably a few more comments or suggestions around the room. I'm happy to kind of throw it to anyone else.
Okay, I can't see any particular hands up at the moment. So given that we don't have an influx of hands up at the moment, can people take themselves off mute?
Can they? I think they can.
Okay, so If you'd like to just take yourself off mute and jump in with a question. Well, no, hang on. We've got Umberto. So over to you, Umberto. Might just ensure you take yourself off mute.
If you're able.
Yeah, I was looking for it. Sorry, I'm not good with this. No, just quickly, I was saying what I answered to Joseph. First, we need to understand how we can measure compliance to 0.1% or some such low number of an online plant. So that is the problem. It already hit me, you know, people asking me, we need to do ongoing compliance. And they said, well, there we go now, you know, the chooks come to roost because it's very difficult. That's all. So first, this is the contingent problem, because if we want to know that the plant is compliant, well, how do we do that? We cannot ask someone to do again hold 0.0 and turn themselves off for 2 weeks, 3 weeks. We're going to pay for that. So this is
I think I'll just jump in very quickly and then hand over to Robert if that the intention was for him to respond. But it's a really good point, and this whole allocation of 0.1%. I mean, when we start to think about practical applications and, you know, being out in the field and determining whether or not a plant is compliant, I mean, you know, a measurement system capable of determining that level of accuracy, you know, at the 48th harmonic order, for example, how much do we trust it? And if we don't trust it, then why are we allocating it? Is my question. That's just a comment from me. Leave that.
Yeah, I agree.
I think the other thing, and it came up in the chat as well, is the level of confidence to get to those smaller numbers at the higher order harmonics. And I can't remember, it was either Joseph or Steve and made the comment earlier that, you know, what is our confidence level of this modeling, not monitoring, but, well, I guess both, once we get up to sort of the 50th harmonic order or the higher band of frequencies that are applicable. All right, we might hand over to Robert, I think is next, Sean.
Yep. Oh, a question for Jason, and thanks guys for the presentations. They're really good. I really enjoyed them. Now, Jason, you led us on the alpha experiment with your wind farms, which is a fabulous experiment to do. I love that. But you brought us to the climax, and you didn't tell me what the alpha value was for the 5th harmonic. What is alpha for the 5th harmonic? This is the highlight of the whole morning.
Look, I fell short because ultimately I cannot confidently tell you. I looked at varying possible values of alpha for the 5th order harmonic, and it ranged anywhere from less than 1 all the way through to hundreds. And as you may know, as the value kind of gets above, I think 5 or 10, it starts to have very little impact on the ultimate calculation itself. So really, the based on the data set that we had, there was not a good enough what's the word? We couldn't really hone in on a good value that gave us a good representation. But I think it's studies like that we need to do more work on, and similar type of work or similar data sets, so that we can, because ultimately if we look at the way that the summation law was developed all those years ago, I think the first publication was in the 70s or something, and it really is kind of this statistical representation over a very long period of time. So if we want to do that, or if we want to gain some level of confidence in these alpha values, and if that's the process that we want to use, then we need much more data rather than just 10 days of a wind farm.
Thanks, Jason.
No worries.
Andrew's next.
So thanks for that, Robert. Over to Andrew Mill, if you can take yourself off mute.
Yep, thanks. I suppose just putting, I suppose, a dose of realism, which is probably where I'm coming from. I mean, we're building assets here for 30 years, 40 years. And we need to know when we're building that we're investing and designing the plant correctly. And I mean, we can only do that with the information available to us at the time. I mean, it's one of the reasons I think, and which with generally speaking, with the power quality side of the NER, it's the only performance standard which is actually allowed to change. All of the NSPs actually say that if you choose a standard less than automatic access standard, we are allowed to actually increase that at any time based on the changing conditions of the network. As such, we aim at automatic access standard. Even so, though, we can design a plant now to be compliant with that, install filters, design the filters correctly. In 12 months' time, it's no longer compliant. Now, fundamentally, there's a problem with that because, I mean, where does the remedy of that sit? Does that mean that we have then, because we are non-compliant, need to go back and install additional filters, change tuning on filters, change the size of filters and the rating of filters because of what somebody else has done? And I suppose that's where we're sitting at the moment with the compliance issue. And I mean, it's always our contribution which gets measured, but we're always looking retrospectively from a point of view of compliance. So we're going back and having a look at the last year's data or whatever it happens to be to determine compliance. We can't go back retrospectively and have a look at background levels because that would have required us to be offline at the same time as we're actually monitoring. So I suppose just some thoughts to go into the future work which you're looking at there. It's that's kind of whatever solution ends up coming up, either with the definition of those levels in the first place, or the method of determining compliance at the back end of it. It has to be a process which is going to work over time. So, and just as a note, just out of interest too, 0.1 is not being used as a minimum by many NSPs. We have numerous cases where we're down to 0.02, 0.03 in our emissions levels.
Yeah.
0.01, I think, even in some of them.
Oh God. How do you meet that?
Yeah, it's impossible to meet. Yeah.
Well, I mean, I guess the opportunity that you would have there is to respond, well, if you can prove that I'm not compliant, then go right ahead. But look, all really good points, Andrew. And this evolving nature and this change, and I mean, it's been mentioned a couple of times now, is a significant challenge, and something that really, when it comes down to it, we need to be practical in our thoughts of how we actually address these issues, because we could go down the road of requiring, these really detailed studies and requiring, 20-year forecasts and requiring this and that and the other. But at the end of the day, what is the risk versus reward? And, if you look at your voltage, your harmonic voltage levels and everything's fine, then is there really a problem? I'd argue not. But it's well enough for us to kind of sit around a table and say that, but writing that into something as prescriptive as the NER or an Australian standard takes a lot of thought and a lot of discussion, so that we don't hurdle down a similar road that we're currently in which we've got a document that is open to a lot of interpretation, and open to a lot of ambiguity and disparate methods being applied, kind of depending on where you were located or what network it is that you're connecting to. But yes, that's just my thoughts.
Yeah, thank you, Jason, and thank you, Andrew.
Thanks.
All definitely concerns that we need to build into the second stage of this project. So, and obviously understand that they're real concerns for you and have been for a while. I think we've got Stephen Zanini next. I was going to say from CQU, but that's not true anymore, is it?
Not for a while now, about 14 years, in fact.
No worries,
Yeah, look, apologies, because I had my hand up to comment on the accuracy issues that Umberto has been raising and the whole 0.1 versus 0.03. So apologies for circling back to that, although I think it's still relevant. We are one of the NSPs that applies the minimum. So we often get through the algorithmic calculation from this, the MV section of the standard, we get allocations well below 0.1. And we then apply the minimum. And of course, then a proponent will come back and say, oh, our measured results are only 0.13%. It's only just over your allocation, but it's wildly over the 0.03 or the 0.01 allocation that came out of the algorithm. So I definitely think there is scope for anything that helps to clarify the uncertainties, to provide more guidance on how we as an NSP can accept. Often proponents will ask us to consider under stage 3, which is, some change of allocation or some allowable exceedance. But as an NSP, we're inherently conservative and we have to be. So I know Umberto has done a lot of work about trying to quantify some of that uncertainty. We'll tend to err on the conservative side. Obviously, the proponent connecting will be trying to err on the less conservative side to allow them. I think anything that improves that uncertainty is a good thing, and that probably should be a focus of some of the work. Most definitely. Any comments on that? And after that, I have a second comment to make, just a general comment.
I'd make a comment just on the use of the algorithm, as you say, and look, I guess part of the overall findings of this project really highlighted that the use of 3-6 builds in a lot of conservativeness already, and there are a lot of, well, I've used the term before, but there are a lot of moving parts, and so to use 3-6 with a lot of confidence, I think takes a lot of input data and a lot of detail, a lot of understanding of the network itself. I've seen spreadsheets and things that have been used that perhaps miss the mark quite substantially, and then others, well, there are some that perhaps are maybe with a little bit more detail, but we don't know exactly the specifics of what's been done. But ultimately, what I would say is that yes, I mean, as an NSP, you need to be conservative at a certain degree, but there is already that conservativeness that is built into the methodology itself, and so it all comes back again to that assessment of risk versus reward, in my opinion.
That's what needs the clarification as to where that uncertainty is, so that we know if we can provide a bit of leeway in this instance because the conservativeness allows that, or no, we shouldn't. In this case, we should err more on the conservative side because I guess some clarity around the moving parts and their impacts and how we can apply those would be fantastic.
Absolutely.
Sean just had a comment to add. Yep.
I'd like to see planning limits change. I don't think they're sensible. I don't think they're sensible in terms of magnitude, nor the way in which they're applied. Why such emphasis on individual harmonic orders? You can have a situation where you've got one harmonic order that's marginally non-compliant. All the others are very much compliant, and you have to do something about that one order. That doesn't make any good technical sense at all, to my mind. So I'd increase them, and then I'd think about how we bundle up harmonic orders into 10 order bins or something like that. I don't have the answer, but they're the sorts of concepts that I think make a bit more sense
and might help remove some of that specific uncertainty.
Correct.
For the NSPs who have to deal with the problems down the track that might occur at extra cost. And I always wish to remind people that when an NSP puts in plant, it's the mums and dads that pay electricity bills that pay for that, as well as the large customers, and so the apportionment of costs and fair apportionment of costs to proponents. My second comment is, 30 odd years ago, people were running around doing a lot of work on active filters, and in particular, something that's close to my heart, hybrid active filters, where you have very small active elements combined with passive filters to improve the performance of the passive filter, to negate resonance. And back then, the research was saying, it's foreseen that once upon a time you had these large harmonic distorting installations connecting in transmission networks where you could do all the studies and have good certainty and blah, blah, blah. But more and more we will see this move down into the distribution networks, and where there is less certainty and much greater potentials for interaction, and because there'll be more of them. And I'm wondering whether that whether the world has seen much movement in that direction, and whether this is the catalyst for perhaps another look at that sort of technology as well, in terms of the harmonic problems. Vic was around in those days, weren't you, Vic?
I'm still around.
Well, actually, Vic, you've brought yourself off mute, so if you wanted to maybe respond to Stephen and ask your own question, if you had one.
Yeah, look, I've got about 3 hours worth to say, but I'll try to attenuate that. Firstly, on the question of limits, the limits, we agree, don't make sense, and you may know that Robert Barr and myself have actually published a paper where we indicate that individual harmonic limits are not the way to go, and we give another approach, but I'm afraid that has received very little reception internationally. Very difficult to push the IEC on limits because they are related to equipment immunity, and if we suddenly start increasing the harmonic levels above that and people's equipment begins to fail, there'll be all sorts of warranty issues. Just touching base for a moment on the question of an installation that be compliant this year and not compliant next year. A lot of this is due to the use of voltage limits and current limits for compliance. I personally believe that voltage limits are of limited value and current limits are in fact totally useless for compliance testing. And there needs to be a different approach, and I think the approach is that the installation must have an appropriate equivalent circuit. And if they've got that appropriate equivalent circuit, and ways are being developed now to measure these online, then if the installation is shown to be compliant 1 year, there should be no doubt that it will also be compliant in the following year. The final thing I want to say is that there is a C-grade working group, 4.40, looking at the next edition of 3.6. I and 2 others of us from Australia are on that committee, and I'm sad to say that COVID has put a real torpedo into the progress of this committee, and I can't see any of the problems that we're talking about today are going to be fixed in the 3rd edition, but maybe young people here may make a contribution to a 4th or 5th edition somewhere down the line. But that doesn't stop us from producing an Australian handbook, and I think that's the only really good way forward. There has to be some Australian handbook that details all these issues. That'll get it up and going much more quickly, and not only that, you've got more chance of influencing the IEC if you've got an Australian guideline that is in use. So that's my 2 hours for now.
Thank you very much, Vic. We'll catch up on the third hour at some point in the future. Look, I do recognise there's quite a bit of chat going on as well. So if people are following that, or if you're not following that, please also look at that as well. We do have one more hand up, which is back to
Umberto. It is.
Umberto, I think.
May not have taken it down.
Do you have
another question, Umberto?
No, just a little observation about the limits. The discussion is for a limit is calculated 0.2%. Okay, great. The plant, after lots of calculations and whatnot, is 0.23% contribution. No, the project can't go forward. Okay, I understand that there is a process that needs to be followed. Then the real problem here is the answer to the what if question. So if it's 0.23 and not 0.2, what is going to happen? Like, I don't think anything, but the problem is that there is a process there. And for the limits, how are we going to, you know, there are limits on equipment maybe 30 years ago. Today's equipment, is it more robust? Is it less robust? I don't know. Here in my house, the voltage waveform is dreadful. Everything functions perfectly. I don't have like my computer power supply blowing up. I don't replace capacitors on the water tank pump and so on and so forth. So I guess that things, especially in a transmission network, are much harder to break, I think, than what we think. That said, contractual obligation towards customers are another thing. But I think we tend to perceive harmonic distortion for something that is way more dangerous than what it is in many cases. So I feel that we can use the asset a little bit more, so we can have a little bit dirtier voltage without any major consequence, and with a great deal of money and struggle saved. But that is to be determined. So if we knew better how much we can stretch it in terms of a distorted voltage, then we can work down towards saying, yes, this limit is 0.something% because we did all this work and because we know that at this frequency, please don't give me a harmonic, otherwise this and that are likely to, you know, have like live for half the time we designed them for. So I think that we need also to look at the source of all the calculations, which is a set of values, as you guys pointed out before, that are that need to be questioned way more than what we question them now. And we could even go down. I'm not saying that they are too low, but that needs to be updated, really. So that's all my comments. And thanks everyone for this workshop. Is really, really good. And thanks for University of Wollongong for organizing. I'm really enjoying it.
Oh, thank you.
Did you have any comment just in regards to, and I'm looking at Sean, in regards to the things that Umberto is talking about and perhaps stage 2 of this project? Like load testing or immunity testing?
Yeah, well, that load testing forms part of what we'd like to do in the next part of this project. So, and touched on what Vic was saying about equipment manufacturers designing equipment to suit certain limits. Part of what we'd like to do is try and understand the implications of harmonics on equipment. If we've done a little bit of work, intuitively, I feel that it's not going to be a big deal. You can have quite distorted waveforms and equipment seems to carry on quite okay. What we don't understand that well necessarily is the loss of life aspects of that sort of thing. What I would say though is I personally believe that magnitude of the supply voltage is much more relevant to an impact on equipment than harmonic distortion for the harmonic levels we've got at the moment, which are generally quite low in Australian networks. So anyway, the long and the short of that is hopefully if we do this project, we might have some answers to those questions.
Yeah.
Okay. Well, I think we're pretty much close to finishing on time. So I recognise that there are still some questions in the chat. We won't try and get through all those questions. I don't think we can do that in the last couple of minutes that we've got. So first of all, I would just like to thank again all our sponsors who are in the original couple of slides that I went through just for supporting the first stage of this project. I would also like to thank any of the proponents and or utilities out there that are willing to support the second stage of this project as well. If you've committed to that already, thank you very much. If you're considering that this might be of use to what you do on a daily basis, we're also very open to having additional people included in that project. I do have the contact details just from an email address point of view, just dropped it into the chat there, but please just look up Australian Power Quality and Reliability Centre and Google will find us from a website and provide you with the contact details if you have any questions at all. So we'll try and, we'll certainly disseminate the recording of this webinar to everyone that's attended today. So you'll have that available to you. We'll try and answer some of the questions that we've left unanswered before we disseminate that, or at least have an attachment which includes that. But I'd just like to thank our presenters again in both Jason David and Sean Elphick for running through the project. And thank you again all for your time, and I will let you get back to the rest of your days. Thank you very much for your time.
Thank you all.
Thank you, everyone.
Thank you. Bye-bye.
Bye-bye, everyone.